So in this video, we're going to start off with the first topic of the course, which is the idea of simple induction. Before we can even delve into that, we're going to do a little bit of a recap, looking at predicates, which I talked about in my one of my previous videos. So again, what is a predicate? Given a set x, or s if you prefer, we'll call a predicate any Boolean valued function defined on x. So it takes an element from the set x and gives you a true or false. So for an example, suppose we got our natural numbers. For all n in the natural numbers, we'll have p of n where n is a multiple of 3. The set of elements where our predicate holds true is a subset of the original set. So for instance, if I have p of n is a multiple of 3, well, the elements where this holds true are a subset of the natural numbers. There are definitely more natural numbers that are not multiples of 3. That is not too hard to prove. But every element where n is a multiple of 3 is a subset of our natural numbers. So this is the first practice question that you'll see in the pre-lecture recordings, and these are here to give you a little bit of time to think about the problems before we take them up in class. So this first problem, which we'll go over in our lecture together, is simply the question of, here are 3 things. Which of these are predicates? And think about it, and we'll take it up in the class. Yeah, which of these are predicates? Okay, why are we using predicates? What's the whole point of this, right? Well, predicates are very important because they are things that we can use, especially when we're actually doing real programming. Consider the following, right? We have some function, sum odd, which takes n, and it computes the sum of the first n odd numbers, and the answer it gives us is n squared. So our predicate here could be p of n, where the sum of the first n odd numbers is n squared. And the claim that we want to have is for all natural numbers, p of n holds. Well, how do we do this, right? How do we show that that's actually the case? If we can show that this is true for all natural numbers, p of n holds, then we can show that the following code is using the right formula, presuming that this whole thing is true. Now, how do you prove a claim holds for different numbers? Well, ideally for all numbers. That's, of course, where the idea of induction comes into play. And the typical example that most instructors, I think, use when it comes to induction is the idea of dominoes, right? I think most people intuitively know how dominoes work. If you stack them all up in a nice little row together, when you tap one, they all fall over, right? But why do they all fall over? Well, here is sort of the idea. Let's suppose we have our predicate, p of n. The nth domino, so the first one is 0, the next one is number 1, then domino 2, domino 3. Suppose we have the predicate p of n, the nth domino will fall over, and so this makes sense for any n greater than 0. I guess we'll say, sure, we'll say the first domino is number 1, and the next is number 2, and so on and so forth. So the first domino will fall over is a statement that makes sense. The second domino will fall over is a statement that makes sense. Can we show that this is the case for all of them? Well, if we're given that I'm going to knock over the first one specifically for you, right? P of 1 falls over is going to be true just by the nature of I'm going to push it myself. So that makes it kind of easy to say, clearly the first domino will fall over. I'm going to push it. Well, yeah, because I'm a rebel. Now we want to say, okay, suppose we have an arbitrary domino somewhere in our chain, right? Well, we know that, assuming that all the dominoes are lined up, if any given domino falls over, it will knock over the one next to it, right? That's just kind of how dominoes work. Well, you can kind of follow this logic, right? Yeah, that's how dominoes work. So you can actually conclude that all the dominoes fall over, and the reason is, if you think it through, okay, well, if any given one will knock over the one next to it, well, I want to knock over the first one. That means that that first one is going to cause the second one to fall over. Well, if the second one's going to fall over, that means it's going to knock over the third one. If that one's going to fall over, it's going to knock over the fourth one. And if you jump down the line and say, okay, well, the first 1, 2, 3, 4 are all falling over, they're probably going to knock over 5 and 6 and so on. At some point, we'll say, okay, we're at the 100th domino. Do you think that one's going to fall over? Probably, right? So if we can assume that that one's going to fall over, what's going to happen to the 101th? 101th? Is that the right way to say it? 101st. Yes, 101st domino. Well, it's going to fall over too, right? do we really need to go through every single domino and like do an analysis of it? Well, no. We can just say we know the first one will fall over. We know for any given domino you look at, it'll knock over the next one. Well, in that case, all of them must fall over at some point. There's no way that any of them are going to stay standing. And that's the idea behind induction. So now that we've sort of informally described what induction is, let's look at a very formal definition of it. So the principle of mathematical induction is a proof method that we're definitely going to use quite a bit in this course, used to prove universally quantified statements about predicates that depend on natural numbers. In other words, we use induction to show that for all natural numbers after a certain point, our predicate holds for all of them. So given a predicate, P of n, and B is the smallest natural number where we actually care about things, in our domino example, let's suppose that we care about basically most of the dominoes falling over, but let's say I don't knock over the first one, I just knock over the second one. Can we still say that all the dominoes are going to fall aside from the very first? Yeah, we can, by the same logic, right? So, given our P of n, and B is our smallest natural number where we actually care about the predicate, the principle of mathematical induction is to prove that for all n in the natural numbers, if n is at least equal to b, then the predicate holds true. So this is the formal definition. Now, any proof of induction is basically divided into two parts. Your base case, or basis case, I call it base case, and your inductive step, which is the second half. And so we'll take a look at some examples of this. So here is sort of the recipe here that we're looking for. For all natural numbers, if n is at least b, then we want to show that anytime the predicate holds for that arbitrary number, it must also be true for the one after it. If we have this, we can then show that it is true just straight up for all of our natural numbers. So the base case here is to prove that our predicate holds true for that initial number. For that very first situation, it must hold, and we have to just do that on its own. The domino is kind of easy. I just flick it, right? But you'll see actually in most cases, the base case, the first step that you do, is usually kind of the easiest one because it's something really simple. Now, after that, we have the inductive hypothesis. So this is the part where we're saying for any n that are at least equal to b, our predicate holds true. We're kind of trying to look at the idea of if we want to say that all our dominoes are going to fall over, right? We know the first one is going to, which will then probably knock over some more. But if we know for sure the first one will fall over, let's just jump right in the middle of the dominoes somewhere and just look at one of them kind of at random and say, okay, what's going to happen here? Let's suppose that that arbitrary one will fall over. Well, what will happen? We know that it will knock over the next one, right? And that's what the inductive step is to prove this part here. For some arbitrary one of our elements that we're looking at, assuming that our predicate holds true, domino falls over, then it must also hold true for the next one, no matter what. And if that's the case, then we basically got things going. Now, it's very important also to make sure that this argument needs to hold no matter what n is, provided it's at least equal to b, and b being whatever number you picked for the base case. So your argument here needs to hold for the base case and show that if the base case is true, then it's true for base case plus 1, but also that it would hold for any arbitrary number that is potentially maybe even much bigger than your base case. So if you can do these three steps, then by the principle of mathematical induction, you can imply that for all natural n, if n is at least equal to b, your predicate is true. Now, why is this a thing, right? Why does this principle work for us? And so it's basically something that goes back to a long dead person who has a property of natural numbers way back from a long time ago, which is that if you have a set with the following properties, where b is in the set, some integer, and for all integers, if k happens to be in the set, then k plus 1 also happens to be in the set. then you can conclude the set has all integers that are at least equal to b. And if you think this through, this sort of makes sense, right? Let's suppose that you have your set, and your set is basically equal to integers greater than 4, right? Okay, well, let's see. 5 is in that set. We're going to say b is 5. Okay, cool. Let's suppose some element is in the set, right? Is the one plus 1 going to be in that set as well? Well, if I take the number 100, right? 100 is in the set. It's bigger than 5. Is 101 in the set? Absolutely. And you can pretty much pick any arbitrary number that's bigger than 5. That number plus 1 is also going to be bigger than 5, which means that all integers greater than b, our initial number, are going to be in that set. So another practice question for you. We want to show that p of n is true for all n. Suppose we've already shown that p of b holds. Which of the following is a valid continuation of a correct proof by induction? There's 4 options here. You can pause this video later on if you want and think about this. We're going to take it up in the class. Okay, so we're going to jump back to an example that we looked at a little bit earlier in this video, computing the sum of the first n odd numbers, which we think is n squared. So our predicate is the sum of the first n odd numbers is n squared, and we want to claim that this is true for all natural numbers. Now, here's how we're going to do it, one step at a time using mathematical induction. So our first step, we're going to prove by induction for all natural numbers n, p of n holds, where p of n is the sum is n squared. Always start off with the base case, and if we're doing natural numbers, base case is 0, right? So we want to think about, okay, what exactly does p of 0 mean? Well, that means that the sum of the first 0 odd numbers should be 0 squared. Well, if n is 0, 0 is 0 squared, which is n squared, so that is clearly true. Okay, cool. We've figured out our first domino. Everything is cool with that one. So our inductive hypothesis is to assume that p of n holds for every for numbers greater than or equal to 0, right? Now, our inductive step is to say that if it holds for some arbitrary n that happens to be greater or equal to 0, then it must hold for p of n plus 1. So, how do we break this down? Well, we know that the nth odd number is equal to 2 times n minus 1. And you can kind of work this out in your head, right? What is the first odd number? It's 1. That's 2 times 1 minus 1. What is the second odd number? It's 3. Well, 2 times 2 minus 1, that's 3. And so you can see it's going up by 2 every time. Okay, hopefully this statement is, I don't have to argue this one too much more. That means that the n plus 1th, or n plus 1th, sure, odd number is 2 times n plus 1 minus 1, which is equal to 2 times n plus 1. Okay. If the sum of the first n odd numbers is n squared, then the sum of the first n plus 1 odd numbers is this plus this. So n squared plus 2n plus 1. Okay, well, we can use a little bit of factoring, because we know math, to take this and say that this is equal to n plus 1 squared. Oh, that's convenient. We've now shown that the sum of the first n plus 1 odd numbers is n plus 1 squared. That means our predicate is true for p of n plus 1. Just by the basis of this argument, I didn't just have to, assume it is true. I've led up to that point. So p of n plus 1 holds for any arbitrary n greater or equal to 0, which means that the proof of our induction is complete. So, by the principle of simple induction, p of n is true for all natural numbers n. Let's look at another example, just so you have some more practice. Suppose we have an unlimited supply of coins that have values 3 and 5, and we want to prove that any integer amount greater than or equal to 8 can be paid using only those two denominations. So you can think of this as basically we only have nickels, and we have these weird coins that are worth 3 cents. And we want to show that no matter what sort of change we need to make, we can make it exactly for any number greater or equal to 8. All right. So hold on, let me move my face out of the way here. It'll put me over here. Okay. So here's our original statement. So what's our predicate here? Our predicate is An integer money amount greater or equal to 8 can be paid using only coins of values 3 and 5. Clearly 8 is like a kind of easy one that we can think of. It's 3 plus 5, so you have one of each. And then can you do the rest of them? Well, before we even like delve into the proof, you can think about it a little bit, right? Could we do 9? Yeah, sure, it's 3 threes, right? That works. Could we do 10? Yeah, we could, right? 2 5s, that seems simple. Could we do 11? Well, we could do 5 and 2 3s. And at some point you can probably stop and convince yourself that this can be done, but we need to prove it, right? So here's our predicate. What's our base case? Our base case is 8. We want to show that for everything greater or equal to 8, we can make it. And we can do that because we got the 5 and the 3. So the base case, we're all good. Now, suppose n is a generic natural number that's greater or equal to 8, and we want to assume p of n holds. This is our inductive hypothesis. We suppose p of n holds for a generic natural number greater or equal to 8. We want to show that p of n plus 1 must also be true if p of n is true. So here's our inductive step. And there's two possibilities. Possibility 1 is that the set of coins that are used to pay contains a 5. If you remove that 5 and add in 2 3s, then you've lost 5 and gained 6. So you've acquired enough to get the next one up, right? So you can see n plus 1 can be paid using only 3s and 5s. You just remove the 5 and add in 2 3s. Great, you got the next one up. Now what happens if you don't have a 5? Well, if you don't have a 5, and you know n is at least 8, that means that n has to be at least equal to 9, right? Because we know we can do 9 with 3 3s. And that means if there are no 5s at all, that means it's all 3s, right, the whole way through. So if it has at least 3 3s, you remove those 3 3s and add 2 5s. So you've lost 9 and gained 10. And so now you've basically increased the amount by 1. So we can get our n plus 1 using just 3s and 5s. And we can conclude that our predicate holds for all n, no matter what, as long as we have the number that we're trying to get is at least 8, we can make it with 3s and 5s the whole time. And the numbers that we use to get up to n, since they already only have 3s and 5s, the changes that we make only include adding 3s or 5s. So the predicate holds. So we're going to finish off with just one last practice problem for you to think about. Consider the following facts about a predicate. P of 1 is true. For all n in the naturals, P of n implies that P of n minus 2 is true. For all n in the naturals, P of n implies that P of 3n plus 1 is true. From the following, select all the correct statements. And here are the correct statements, potentially correct statements, that you can pick from. For all n, P of n, P of minus 2, P of minus 1, P of 0, P of 1. And you can think about which of these might be true, which of these might be false, and we'll go over it in the class.